Now let me introduce you what exactly you mean by adjoint of a squared matrix. And then it will be required to find the inverse of a squared matrix. Though we have already done how to find the inverse of a matrix using elementary row or column transformations. But this time we'll use it using adjoint. So in exam you may be asked to find the inverse of a matrix using elementary operations or elementary row or column transformations, or maybe it is specified that find the inverse of a matrix using matrix method or using adjoint. This is known as using adjoint or using matrix method. And normally it is a 6-mark question. So let me define what do you mean by adjoint of a squared matrix. Let's suppose given is a squared matrix A, Aij of order n, that is n by n. Then how do you define adjoint A, denoted by the symbol Adj? Adjoint A is defined as transpose of another squared matrix of the same order n by n obtained by replacing each element Aij by the corresponding cofactor. Adjoint A is defined as a squared matrix n by n Cij. What is Cij? Cofactor of Aij. If you have like A11, A12, etc., so it will be C11, C12, etc. Each element is to be replaced by corresponding cofactor and then take transpose of it. For example, let me take a symbol in a broader sense, that if the given matrix A is A11, A12, A21, A22 of second order, then adjoint A will be obtained if you replace each element. That A11 you write C11, C12, C21, C22 and take transpose of it. That will be adjoint of the matrix. And now let me take a numerical example. Suppose given is a matrix A equal to 2, 3, 1, 4. Then what is adjoint A? You know, symbolically it will be transpose of C11, C12, C21, C2. Let us work out all these cofactors. You know the sign conventions, plus, minus, minus, plus. That means C11 is what? You delete the row and column through one element. So let me write here. C11 will be delete the row and column through 2. So you left with 4, the opposite element, and it will be taken with plus sign. So it will be plus sign. It will be plus 4. Then what about C12? Delete the row and column through C12, that is the 3, and what is the opposite number? 1. But for C12, what is the sign? Negative. So C12 will be negative 1. And then what about C21? This is your C21 place. This one. This is C21. Delete the row and column 3 C21. So you left with 3. C21 is 3. And what about the sign for 3 to 1? It is negative. And finally, let me take C22. C22. C22 is this place. So you delete the row and column through C22. You get the opposite number, which is 2, and it will be with positive sign. So if you replace all these, then the numerical value for the given matrix A, adjoint A, will be, never forget transpose. Transpose of C11, which is 4, and C12, negative 1, and C21, which is negative 3, and C22 is 2. And take transpose of it, and finally you get the value of adjoint A as 4 minus 1. When you take the adjoint, the elements of first row will go to first column. So it will be 4, negative 1 like this, and negative 3, 2 will go to the second column. So let me write once again. the value of adjoint A is 4 minus 3 minus 1, 2, and what is the order? Order remains 2 by 2. So that is about the method of finding the adjoint of a matrix of second order. For second order matrix, we can have a ready-made method to learn it also. Just see, please make a note that if you are given a matrix, say A, B, C, D like this, then its adjoint, as we just now worked out, how do you do it? That you take the cofactor of A as D, that of D as A, and both will remain positive, C of B with negative sign and B of C with negative. And now you take the transpose of it, you get D minus C, you get here, write it here, D, the elements of the first row to be written in first column and second row in second column. What do you find here? Do you find that the elements in the main diagonal A and D have simply been interchanged? Just interchange the elements of main diagonal to get the value of adjoint A. Please note down, if you are given a matrix A, B, C, D, then to check the adjoint A, you just interchange the elements of the main diagonal, and what about the other diagonal? Just change the sign. The elements on the other diagonal, you just change the sign. The elements will remain the same, only their signs will be changed. So that is a shortcut way of finding or checking the adjoint of a matrix of second order. Now note down another important result. Let me call it theorem 1. It can easily be verified for any given, if A is a squared matrix, then A into adjoint A, even for this numerical example you will check, A into adjoint A equal to adjoint A multiplied by A will always be determinant A multiplied by the corresponding identity element of the same order. So this is an important result which will help us to find A inverse later. Now note down two definitions. Definition 1, what do you mean by singular matrix? Singular matrix. A squared matrix A is said to be singular if determinant A is 0. And what do you mean by non-singular matrix? Non-singular matrix. Again, a squared matrix A is said to be a non-singular matrix if determinant A is not equal to 0. Then you note down a theorem 2. All these results I am giving ready-made to you, considering will be required directly. If A and B are non-singular matrices, if A and B are two non-singular matrices, then the product AB and BA, these two matrices, are also non-singular and of the same order. That means if A and B are two non-singular matrices of the same order, then AB and BA are also non-singular of the same. That means if A and B are of second order, then so will be BA and AB. And if A and B are of third order, then BA and AB will also be of third order. Now next result. If A and B are square matrices of the same order, A and B are two squared matrices of the same order, then the determinant of the product AB will be the determinant value of A into determinant value of B. The another result, please make a note here, that if A is a non-singular matrix of order n, if A is a non-singular matrix of order n, then the determinant of matrix adjoint A, after all adjoint A is a matrix, so its determinant value will be the determinant of A to the power n minus 1. For that, by that you mean, for example, if A is a matrix of order 3, that is 3 by 3, then the determinant of adjoint A will be determinant A square. Next result. What do you mean by invertible matrices? You already know. Invertible matrices means given is a matrix A, if we could find out another matrix B such that AB equal to BA equal to identity matrix. So note down a result, say theorem 4, a squared matrix A is invertible, means it is inverse exists provided A is non-singular. Provided A is non-singular, that means determinant A should not be equal to 0. Then only we can find the inverse of matrix A. And now finally, let us define numerically using adjoint and hence the matrix method, how do you find inverse of a squared matrix, which is very important, and even will have solving system linear equations using the inverse, that is matrix method. It will be required. First of all, you note down the definition. Given is a non-singular squared matrix, remember, then A inverse is defined as 1 by determinant A into adjoint A. The proof is simple. Just now you had noted. Why so? You had noted that any squared matrix A multiplied by its adjoint A can easily be verified, gives you determinant A times identity matrix of the same order. After all, determinant A is a number. So it may be rewritten as that matrix A multiplied by its adjoint divided by determinant A gives you identity matrix. So what do you find here? Here you find that adjoint A by determinant A is a matrix of this kind, that given is a matrix A, if we can work out another matrix B such that A into B equal to B into A equal to I, then what do you say? That A inverse is B. So what is in place of B here? It is adjoint A by determinant A, because A multiplied by adjoint A into determinant A makes you identity matrix. So this is the result, that if you have to find out A inverse, you work out adjoint A and divided by determinant A, which is a number. Now please make a note that AB inverse, that is the inverse of product of two matrices A and B, the squared matrices of the same order, is the product of their inverses in reverse order. You had a similar result for transpose also, if you remember that AB transpose is B transpose into A transpose. And also make a note of another important result which I have discussed with you earlier also, that given is a matrix Aij of third order, say 3 by 3, then the determinant of Ka will be K cubed times determinant A. It has been discussed in the previous exercise in detail, but you may require it here again. That's why I am giving you this particular result.